So 3.4 economics, we're starting off with this equation where C of X, this part here, is looking at the cost of lumber, the cost per unit to produce lumber, so C of X, that's what it represents. And X represents the number of units. I'm going to actually write that down. So this is the number of units. And I guess just to write it briefly, this is the cost per unit. Okay, so we're given the equation. This is for a milling company that cuts down trees and mills up lumber for sale. So basically all this is the same old stuff that we've been doing. So we're looking at derivatives, but now we're getting to see the different applications of it. That's basically what this entire chapter is, right? So in the first one, you did velocity, right? Second one, you did acceleration. So again, like I was saying, most of the stuff is usually related to math science type of stuff. So this time you get to see an economics application of the same old stuff that we've been doing. So if we wanted to take a look at some of the information for this, we could set it up as per usual with a table of values. And it doesn't really matter, but we could start, let's say, with 0 for our X value, and our C of X would then be 90. If we had 1, we would get 70. If we had 2, it would be 63. 3 would be 60. You all know how to plug this in and spit out numbers, so I'm not going to spend time going over that. I'm just going to give you some values so that we can start to look at the pattern of behavior, which is always ultimately what we're interested in. So if we were to take this and take a look at what this would work out to on a graph and look at the trend or the pattern of behavior that way, I'm going to put our 50 here because of this plus 50. Basically, we have a pattern of behavior. So it starts at 0 and 90. And what ends up happening is it ends up looking, oh gosh, that looks awful, something like this. So we would be looking at this information to help us to understand what it is that's happening. So on the y-axis here, of course, would be cost, which is the part that we talked about here. And over here, we would have the units. So we're trying to figure out or analyze this data to help us to determine what it is that's happening. So we look at the cost, we can see up here, the first units are going to be expensive, right? And then as we go this way in direction, so as we get to more and more units, the cost starts to decline a little bit. Make sense? So, and you'll find this is, I don't know if you've done much to do with economics, but this is usually the case with most things. It's cheaper to make more, usually, right? So similar to if you're looking at it on the receiving end, if you're someone who is looking to purchase something, that's why it's usually cheaper if you buy more, buy in bulk, but the fewer that you have, the fewer that you make. In this case, it would be a little more expensive. Okay, so that's what that's showing. And then if we want to take a look at this from a calculus perspective, we can take this equation up here and we can look at the derivative of this equation. And so taking a look at the derivative of this equation, do you see that we can take all of this and find the derivative of that, and we end up with negative 40 over x plus 1 squared. I didn't spend time going through that, but does everybody see, just really quickly, I guess I'll show you off to the side here. Do you see that I could rewrite that to say 40 times x plus 1 to the negative 1, and then go through and do the derivative so it makes sense? And that was something that we sort of the last day I was here, so I guess Wednesday, we looked at, I showed some people instead of doing the quotient rule with some of the questions that you had, it's often easier to just move this up and change it to a negative exponent and go through the power rule to basically reduce the amount of work you have to do. Take your pick. It's up to you, whatever you find easiest to work with. Okay, so this would be the derivative, and what this c prime of x, we would call this the marginal cost. So I'm going to put a little star beside that. The marginal cost in economics means the slope or the derivative of the function that you're working with. Good? Okay. So, if to take a look at an application of this, I feel like you probably don't need this, but we will. So let's say we want to find, for example, c prime of 3. That just means we plug it in. We would, into our equation, say negative 40 over 3 plus 1 squared. So do you see that we would just get negative 10 So we'd have negative 40 here, and we'd have 16 here, right? So if we reduce that, well, this is weird because it looks like a negative. We'll talk about this. Negative 10 over 4. What this is telling us is, do you see that this would mean that by the third unit, so where am I getting that from? This c prime of 3 that I plugged in, that's where that's coming from. The costs are decreasing by $2.50 per unit. I feel like I shouldn't have put a circle around that. Maybe it makes more sense if I change it to negative 250 there. So you'll find this often in calculus. Things that we never used to use negatives for, like time, like money, we now can have, but it usually means we're looking at it with a little more depth. So that negative usually tells us a little more information about what's going on. So there's the application and what we might use the derivative for, to find the marginal cost, and this shows you what exactly that even means. So you do need to know, if I ask you questions about marginal cost, for example, so there's a concept thing, you need to know what that means, and you need to know that means taking the derivative. Good? Okay. Yes? Yeah. Yes. Yeah. Yeah, does that make sense? Connect it to that? Yeah, good. Okay, on to the next concept. We have P of X equals 300 minus X over 2. This is the price function, or sometimes called the demand function. X again represents the units sold. So just to, again, quickly show you what this would look like if we were to sketch out a graph to make sense of this. Obviously, if we plug in 0 for X, we can see that this would be at 150 when we're talking our price. And then as we would move our way down here, this would be units sold. This would be at 300. So, fewer units sold would be more expensive. It's the same pattern of behavior. Down here, cheaper prices equals more units sold. Make sense? And logically kind of makes sense, right? Okay. And then we have our revenue function. We have R of X equals X times P of X. So this is our revenue function. Which is money earned. X would be units sold again. Units sold. And this P of X would be the price. So, referring back to what we did here, we would have this equals, I'll write that in the same value, 300 minus X over 2, so I got that from right here, times, whoops, I should do the right color, times our X value. Good? And then let's look graphically at how this would show up. So let's say we have a graph that looks like this. There's our 300. There's 0. Here's our revenue. and here's our units. So let's interpret this. What's that point? Although it's lopsided. Pretend it's perfectly symmetrical. Revenue is how much money you've made, right? So this would be our maximum revenue. And if down here, this is like finding balance between how much it costs to make the stuff and how much you're selling it for, right? And then how that relates to revenue. So down here, we sold it too cheap. So you would use this, or companies would want to use this to figure out the optimum price to set something at. Do you see that it's all about finding balance? Because you want to make enough money off of it. You want to sell it expensive enough that you're making enough money off of it to cover the cost of making it, but then you don't want to make it so expensive that no one's going to buy it, right? And so you want to make it cheap enough that people will buy it, but not so cheap that it's not even covering the cost of making it or producing it. So it's sort of like a balancing act, much like so many other things that we talk about. Okay, so then on to the next thing. Well, actually, let me tie it in here. So see this maximum revenue that we just talked about? We want to look at how to find maximum revenue. The maximum revenue is when the slope of r of x equals 0. That makes sense. Do you see where we're looking at up here? We know from before that the slope at that point would be equal to 0. So we don't necessarily need the graph, but I feel like getting that visual of what's happening helps us to understand the information. So if we have r prime of x equals 1/2 negative 2x plus 300, to take the derivative of it, and then actually let's simplify that. Do you see that we can simplify that to just make it negative x plus 150? I'll rewrite that. R prime of x equals negative x plus 150. Maybe it's also helpful to know that this would be our marginal revenue. We already talked about marginal cost. Marginal anything is us taking the derivative Okay, to put things into perspective, do you see we have a couple of new equations we're working with, but do you see it's still us doing the same old thing? So we took this r of x equation, we take the derivative of it, and then to find the maximum revenue, what do? Take the derivative and now what? Set it equal to 0. Do you kind of see what I mean? That it's just the same old thing as always? Slightly different form. Oops, I forgot the negative. Set it equal to 0 and then we use it to solve. So basically just slide the x over and we would get x equals 150. So basically since this is an application, what does that 150 represent? 150 units sold to maximize revenue. Does that make sense? That's what we just found. So we took the equation, found the derivative of it, set it equal to 0, and then we solve to find the number of units need to be sold to maximize the revenue. So then let's plug that into way back here where we had the price function. So let's do P of 150, now that we just found that 150 is the amount that we would need. And when we plug that in, we find that it's equal to $75 per unit. So plugging it back into this P of X function, when I plugged in 150, that's what we found. 150 divided by 2, that's how I got this $75 per unit. R of 150 is the revenue, remember? So when I plug this into my R of X equation, so before I took the derivative, so this part here, I find that I get $11,250. Which brings me to the last equation that I think you'll find kind of makes sense based on what we've done. This profit would be equal to the revenue minus the cost. So this is our revenue, and this is our cost. It makes sense, right? That the profit would be the revenue minus the cost. That's kind of just common sense if we think about it. So our P of X would equal, I'm just plugging in the previous equations that we've already gone through. We had our R of X was 300 minus X all over 2, times X. I don't know what is going on with my brackets. There we go. Minus my C of X, the cost equation from, if I scroll back, you'll find it. It was 40 over X plus 1, all plus 50. Good? And if we clean this all up, we get 1/2 x squared plus 150x minus 50 minus 40 over x plus 1. We're following the same pattern as what we've been doing all along. So if I look at this overall profit, this overall equation we just came up with, and I want to find the marginal profit, what would I do? Take the derivative. So basically, P prime of X, and when we do that, we would get negative x plus 150 plus 40 over x plus 1 squared. This is one of those days. I need you to check my work. That does look right. Does that look right? Okay. And then, same pattern as before, what comes next? Set it equal to 0. And same old thing, plus 150 plus 40 over x plus 1 squared. Well, we don't want this over x plus 1 squared. So do you see that I could take this and set this like negative x plus 150, multiply that by x plus 1 squared, the whole thing, in order to, so basically I'm multiplying the whole thing, all of this, by x plus 1 all squared. But in doing that, I've wiped out the bottom part here, right? So that's all I've done in order to not have a fraction and to start to clean things up a little bit. But what I'm finding when I go through this, when I multiply this all out and distribute it, so if I do this times this, well, I'd have to first do x plus 1 times x plus 1 and then multiply it by all of this. I'm going to get negative x cubed plus 148x squared plus 299x plus 190. This is a cubic equation. Like normally the next thing would be looking to see if we can factor this and using that to simplify and find the answer, right? But we have a cubic equation. Do you remember cubic equations from pre-calc 12? Okay, no big deal. What we would want to do is we could plug this into a graphing calculator to get a visual image of what this looks like in order to solve it. Or later on, we could use something called Newton's method, which we would learn. But as of right now, I'm just going to tell you that the solution, if we were to plug it in, would be at x is around 150. So we wouldn't algebraically figure this out because it's too complicated. Yeah. Okay, do you see that this is the same old thing as before, except today we looked at, I guess, a few new concepts, right? So knowing about profit, knowing about revenue, knowing about how to find marginal profit, marginal revenue, marginal cost, all of that stuff, but which is basically just taking the derivative, setting it equal to 0, and solving it. Page 139, numbers 1 to 4 and 6 all.